Welcome to this video on the basics of deep learning. We will explore key concepts, theory, the training process, common architectures, and how to evaluate model performance. This video follows a clear path from intuition to practical training. Our core message is that deep learning models learn useful internal representations by adjusting numerical parameters to reduce prediction error. A neural network is a function that learns from data. Unlike traditional programming, which relies on explicit rules, deep learning models learn the mapping directly from examples, making them highly effective for complex patterns. Deep learning is a specialized family within the broader field of machine learning. It is particularly powerful when dealing with large, complex datasets that are difficult to describe using manual, handwritten rules. At its core, the learning problem involves using a dataset to estimate a function that maps inputs to targets. The goal is to choose model parameters that minimize error, while ensuring the network generalizes well to unseen data. The basic building block is the artificial neuron. It computes a weighted sum of its inputs, adds a bias, and applies an activation function, which introduces the nonlinearity necessary for complex learning. When neurons are arranged in layers, they form a hierarchical structure. Early layers capture simple, local patterns, while later layers combine these into complex, high-level features, automating the process of design. Activation functions are essential for giving networks their decision-making power. Common choices like RealU, sigmoid, TON, and softmax serve different purposes, from hidden layer transformations to producing specific types of outputs. Loss functions quantify the model's error, providing a value that optimization algorithms can minimize. Whether it is classification, regression, or sequence prediction, training focuses on steadily pushing this loss downward over time. Gradient descent is the primary optimization technique. By adjusting weights based on gradients, the model learns. The learning rate is critical here. It controls the size of each update step, influencing the stability of the training process. Backpropagation is the efficient method used to calculate these gradients. By applying the chain rule and reusing intermediate values, it allows the network to learn far more quickly than if it were updating weights in isolation. Training happens in a loop, typically processing data in mini-batches. This sequence includes the forward pass, loss computation, backpropagation, and weight updates, followed by periodic validation to monitor performance. Data preparation is vital, as quality dictates model success. After collecting, cleaning, and labeling data, we split it into training, validation, and test sets. It is crucial to avoid data leakage to ensure evaluation remains valid. Different architectures are suited to different data structures. MLPs, CNNs, RNNs, and transformers each have their strengths. A good rule of thumb is to start simple and only increase complexity when your data supports it. Finally, transformers use self-attention to understand relationships between tokens in a sequence. By stacking these blocks, modern models can process information in parallel, though this does come with computational costs to consider. A major challenge in deep learning is overfitting, where a model performs well on training data but fails to generalize. To combat this, we use regularization methods such as data augmentation, dropout, and early stopping. Choosing the right evaluation metrics is essential. Whether you are performing classification, regression, or text generation, select a metric that aligns with the real-world cost of mistakes. Always perform a thorough error analysis. Hyperparameters like learning rate, batch size, and network depth significantly impact performance. The best practice is to keep a stable baseline and change one major factor at a time, documenting each result carefully. Reliable deep learning requires an iterative workflow. Define your task, prepare data, build a baseline, train, analyze your errors, and then improve. Log everything so you can track your progress. In summary, deep learning is powerful when your data, architecture, objective, and evaluation are all aligned. Thank you for joining this overview of deep learning principles and practices. This video summarizes what we have learned. We have covered the fundamental building blocks of deep learning and how they function together. Deep learning is fundamentally about representation learning. The process of automating feature discovery is what sets it apart from traditional algorithmic approaches. We explored the training loop, the heart of the model's evolution. It balances forward passes with backward error correction to refine its internal parameters over time. Data discipline is non-negotiable. Whether it is cleaning, labeling, or splitting, your model's success is tied to the integrity of the data you provided. We reviewed how architecture choice must mirror the task, using the right tool for the job. whether a CNN for vision or a transformer for sequences, is key to efficiency. Generalization remains our ultimate goal. By using techniques like dropout and early stopping, we ensure that models do not simply memorize the training data, but truly learn patterns. The workflow we discussed is iterative. Start small with a simple baseline, then refine your strategy through careful error analysis and systematic experimentation. Deep learning thrives on alignment. When your data structure matches your architecture and your metrics reflect your real-world goals, you achieve high performance. Remember that hyperparameter tuning is a science of its own. Change one variable at a time and document your results to avoid confusion. The shift from rule-based AI to learned representations has revolutionized technology. Understanding these basics allows you to navigate this complex field more effectively. As you continue your journey, keep focusing on the fundamentals. The tools and frameworks change, but the core principles of optimization and representation remain constant. Always prioritize clarity in your evaluation. A model that performs well on a metric that does not matter is not a successful model. Documenting your experiments is the hallmark of a professional. Keeping track of seeds, code versions, and failure cases will save you hours of redundant effort. The field is rapidly evolving, but the core concepts we have touched upon in this video provide the solid foundation needed to keep up with new breakthroughs. Thank you for watching this series. You now have the essential building blocks to start exploring, building, and refining your own deep learning projects. Let's explore the learning map. Deep learning becomes manageable when you organize the stack into 3 distinct layers: core concepts, specific architectures, and applied systems. First, we focus on foundation. Neural networks don't store manual rules. They learn internal numerical representations that make prediction easier and more robust. The core mechanism is the training loop. It is a cycle of passing data through the model, calculating the loss, performing backpropagation to find gradients, and updating parameters. Next, we consider architectures. Each model family imposes a specific bias on the data. Choosing the right one is essential, because the wrong architecture makes learning unnecessarily difficult. Transformers are a powerful architecture where attention replaces fixed memory. Every token can look at other tokens to decide what is important for the next representation. In practice, most systems use pre-training followed by fine-tuning or parameter-efficient methods. This allows models to adapt broad representations to specific languages or tasks. At the inference stage, decoding turns model scores into text. Whether using greedy search or beam search, the process determines how the model traverses the token tree. A critical failure mode to watch for is catastrophic forgetting. When fine-tuning, you must ensure that learning a new task does not damage existing capabilities. Multimodal learning combines different types of input, such as audio, spectrograms, and annotations. Integrating these signals allows the model to leverage complementary information. Whether working on translation, ASR, OCR, or retrieval, the pattern remains the same. Focus on data quality, model choice, training protocols, and rigorous error analysis.